Hello, it's Malcolm here, and in this screencast I'm going to introduce you to the thinking and working mathematically process that we've called convincing. To begin this discussion, look back at the warehouse problem from problem set from week 2. So the one where it says you've got a purchase price and you're wondering, is it better to add the sales tax of 15% first and then calculate the discount of 10%, or the other way around? Now, when we did this, we started off by specialising, most of us did anyway, and we probably used a simple price like $100. And what we found as a result of that specialisation was that we got the same value no matter which order we did the calculations. For some of us, that was good enough and we stopped there. Others of us said, well, maybe I need to try to specialise with some different prices and maybe just choose a number at random, so something like $30, for example. And when you did that calculation, again, the order of the calculation made no difference. And so at that point, we probably made a conjecture, something along the lines that says, no matter what the purchase price is, the sale price will be the same regardless of which is calculated first, the tax or the discount. And of course, this conjecture is a generalisation of the problem as we solved it with the $100 and the $30. And so now we've made a conjecture and we've made a generalisation. What do we do now? So quite often at this point, the non-expert's happy to stop. They said, right, I know what's going to happen in this problem, I'm always going to get the same answer. And that's good enough for them. However, the research shows that for the mathematician, they aren't happy at this point. They say, yes, I know for $100 and $30 I get the same answer, but is it possible there could be some other value, like $913.26, for example, for which we don't get the same answer? It's that skeptical attitude that defines a mathematician. And so the mathematician at that stage says, okay, look, I really believe this conjecture is true, but what I need to find is an argument that says that it is true no matter what purchase price we use. And so the next thing that the expert mathematician does is try to produce that convincing argument. So how would we go about doing that? Well, in this case, we can go back to our specialisation and that will help us. Have a look at the problem and how we solved it with $100. So let's calculate the discount first. We said $100 minus the 10% discount, and that gives us $90. And then we added the tax to that, so $90 plus 15% of $90, and we get $103.50. Now, we can do that exact same calculation with a general purchase price, say, of P dollars instead of 100. So here we go. Calculate the discount first, and you get P minus 10 on 100p, so that'll be 90p on 100. Now add the tax, 90p on 100 plus 15% of that, and if you get good at your algebra, you'll get something like 115 times 90 over 100 times 100, lots of p. If you now do the calculations the other way around, you get exactly the same expression. And so here you have an argument that holds for any purchase price. Of course, to be able to do this argument, you have to be proficient in algebra, and that's not for everybody. I don't know, if you didn't have algebra skills, what would you do at this stage? Well, there's a couple of things. You might give up and say the problem's too hard for me, or you might ask around and find some people know algebra and find that they can help you and they'll teach you, or you might search around and find algebra on the net or something and teach yourself. Or if you were really bright and you were really persistent, you might end up inventing some algebra for yourself, inventing some new mathematics to solve this problem. Of course, that's not the kind of thing I expect from you, but they are the possibilities. There are a couple of things worth noting about our convincing argument for the warehouse problem. Firstly, the convincing argument used algebra, and hence it contained a lot of symbols and equations. That's not always the case for convincing arguments. That won't always happen, and neither should you expect it to. The second thing to say is, in this case, we came up with our convincing argument pretty much first go. That's because, in this case, I was fairly fluent in algebra. But I would say to you, this is the exception rather than the norm. Normally you won't come up with a convincing argument first go, and certainly you wouldn't be able to write it out first go. It takes a lot of practice and a lot of hard work to get a convincing argument up to speed. And the last thing that I wanted to point out about the convincing argument is that here our specialisation, what we did when we specialised, guided our construction, and that was very helpful. However, once again, you shouldn't expect this always to be the case. Certainly go back and have a look what your specialisation helps you with, but it may or may not help you come up with your convincing argument. Consider now the problem of determining the sum of the angles in a triangle. Now, we all know that the sum of the angles in a triangle is 180 degrees. How do we know this? Well, we were told in school and we've had it drummed into us ever since. But imagine that we didn't know this for a fact. How would we go about trying to create a convincing argument that the angles do add up to 180 degrees? Well, or even what the angles add up to. You'd start off by specialising, and you'd draw a triangle, you'd measure the angles and see what they add up to. And you would find that the angles nearly always add up to 180 degrees. There'd be errors in your measurements and you wouldn't quite get 180 degrees, but it might be enough to make the conjecture that the angle sum is always 180 degrees. So now you're trying to make your convincing argument up, having done your specialisation, your generalising and your conjecturing. And you go back to your specialisation and say, okay, what did I do? Well, I measured the angles and then I added them up. That doesn't seem to help you make a convincing argument. So let me now go through with you a convincing argument that is general. It holds for any triangle, doesn't matter what triangle you use, and it will prove that the angle is exactly 180 degrees. So if you start off with triangle ABC, you construct a line parallel to BC, say, and passing through A. And let's call that line the line DE. Now, since DE is parallel to BC, angle BCA is parallel with angle, not parallel, is equal to angle EAC. And that's because alternate angles on parallel lines are equal. Similarly, angle CBA has to be equal to angle DAB. Again, because alternate angles on a parallel lines are equal. So now angle DAB plus angle BAC plus angle EAC have to add up to 180 since these angles form to combine a straight line. Combine to form a straight line, I should have said. Now, because those angles are equal, we can see that angle CBA plus BAC plus BCA add up to 180 degrees. And so there is a convincing argument. It holds for all triangles, but it came from nowhere near what we did when we were specialisation. So how did the person or persons that came up with this convincing argument actually come up with it? Well, I suspect they probably had a lot of experience with geometry, and they knew that adding construction lines is quite often a helpful thing to do. They probably also knew things about parallel lines, and they wanted to make use of those facts. And so putting all those together, somehow or other, creatively, they came up with this idea. So you can see in this case, their specialisation didn't help. And so there's still a lot of work for the mathematician to do, even though they might have an idea of what the answer is. We're going to talk more about convincing arguments in class, but let me just finish off this screencast by emphasising that coming up with convincing arguments is an essential part of the culture of mathematics. It's part of what makes mathematics different to the other sciences that we study.